character tables confuse a lot of people, so let's go through them in a way that feels natural. Take a simple molecule like H2O. Every molecule has a set of symmetry operations, things like rotations, reflections, or inversions, and the complete set of these operations defines the point group. That point group is basically the molecule's symmetry code. Now, usually we think of applying symmetry to the whole molecule at once, but H2O isn't just one blob. It has different molecular orbitals and different types of motion, like bending or stretching. And here's the catch. Not all orbitals or motions behave the same way under this symmetry code. Some orbitals stay the same, some flip, some mix with each other. So instead of treating them all together, we use a character table to sort out the different types of symmetry behaviors. This is where irreducible representations or irreps come in. Think of an irrep as the smallest unit of symmetry behavior, or a pattern that tells you exactly how something corresponds to every symmetry operation in that point group, and each irrep gets its own row in the character table. Here's another way to think of it. Imagine the molecule is a band. Each irrep is an instrument like drums, guitar, or vocals, and each symmetry operation is like applying an effect to that instrument. Not every instrument reacts the same way. The drums might not change under all the effects. That's like the orbital staying the same. The guitar might invert with some effects. That's like the orbital flipping sign. And the vocals might mix into harmonies. That's like functions combining. So each instrument is defined by its characteristics or how it reacts to this effect, just like irreps are defined by how they react to symmetry. So going back to the character table, what do the numbers in this table actually mean? Well, again, they are the character of the irreps. So if we have +1, that means unchanged. If we have -1, that means the sign is flipped. Think of a wave function inverting. If we have 0, this means they mix or move into other orbitals. And if we have +2 or -2 or greater values, this is multi-dimensional irreps. So going back to H2O, let's see what irreps these molecular orbitals belong to. For this one, it stays unchanged, so we have A1. For this one, it flips under C2 rotation or sigma YZ reflection, so we have B1. For this one, it stays unchanged, so we have A1 again. For this one, it flips under both C2 and sigma XZ, so we have B2. For this one, again, it stays unchanged, so we have A1. And for this one, it flips under C2 rotation and XYZ reflection, so we have B1. So H2O's molecular orbitals fall into A1, B1, and B2. But wait, what about A2? Well, none of H2O's molecular orbitals actually use it. So why is it in this table? Well, this is where the confusion comes from for a lot of chemists trying to understand where we get character tables from. It's about the math. Irreps don't come from the molecule, they come from the point group symmetry itself. So group theory guarantees that C2V has 4 irreps, A1, A2, B1, and B2. And I'll leave a brief mathematical explanation in the comments. Otherwise, think of the table as a toolbox, and its irreps are the tools. So for H2O orbitals, you can use A1, B1, and B2. For vibrations, you can use B2. For rotations, A2 shows up, and other molecules in C2V might need the whole toolbox. So essentially, the toolbox always comes with all the tools, and you just use the ones you need. So what about all these letters that represent the irreps, and what about all the other symbols we see? Well, these are Mulliken symbols. Each Mulliken symbol, A, B, E, and T, describe both how the orbital behaves under symmetry operations and its dimensionality or degeneracy, where its degeneracy is how many orbitals share the same energy level. For the main symbols, A is one-dimensional and singly degenerate, so only one orbital, and that stays the same when we rotate it around the main axis. For B, it's one-dimensional and only has one orbital, but it changes sign when we rotate it around the main axis. For E, it's two-dimensional or doubly degenerate, and two orbitals act together. For T, it's three-dimensional or triply degenerate, and three orbitals act together. For the subscripts, if we have a 1, it's symmetric with respect to the main axis. If there's no main axis, it's symmetric with respect to the vertical mirror plane, or sigma v. For 2, it's anti-symmetric with respect to the main rotation axis, or for sigma v if no axis is present. For G, or Girard, it's symmetric through the center of the molecule. Or for U, which is un-Girard, it's anti-symmetric through the center of the molecule. For the prime symbols, if we have 1 prime, it's symmetric when reflected across a horizontal mirror plane, or sigma H. For 2 primes, it's anti-symmetric when reflected across a horizontal mirror plane. So when we say this orbital in H2O has A1 symmetry, it means it's one-dimensional, it's singly degenerate, it's symmetric with respect to the main rotation axis, and it's totally symmetric under all the symmetry operations of the C2V point group. So there's no G or U here because the inversion symmetry doesn't exist for this point group. Okay, what about the linear, rotations, quadratic, and cubic rows? These rows are basically a quick guide. They show which shapes, motions, or functions behave or transform the same way as each irrep. Or in other words, find your orbital, vibration, or function in one of these rows, and that tells you which irrep it belongs to. To describe this in more detail, I'll go through them one by one. For linear functions like x, y, z, these describe simple directions, like the axes of a molecule. In C2V, z equals a1 because z doesn't change under any symmetry operation. You can see how the only axis that doesn't change is z. So if you have anything with this property, it's a1. These also tell you vibrational information. So for example, if a vibration changes the dipole along the z-axis, yes, the shape changes, but the orientation of the z-axis doesn't change. And if we freeze it at any point in time, all the symmetry operations can still be applied. So polarization along the z-axis will give us A1, and we have IR active molecule with A1 symmetry. For those other axes, it's the same. If it's X, we have B1. If it's Y, we have B2. For rotations, these represent any twists of the molecule around each axis. So if an irrep lists RZ, for example, that means that all symmetry operations we can apply will be the same rotation direction, the same as its irrep, in this case A2. So if anything's rotation along the z-axis will stay the same with E and C2, but change the rotation direction with sigma xz and sigma yz, it will be A2 symmetry. For quadratic functions, these are two axis combinations often found in d orbitals. If an irrep includes any of these, vibrations in that irrep are usually Raman active, so they scatter light rather than absorb it. And just like with linear functions and rotations, if an orbital or vibration remains unchanged under any operation, for example x squared stays the same, it has A1 symmetry. Cubic functions. These are three axis combinations similar to F orbitals. They mostly appear in higher symmetry groups, so you don't really need them yet for smaller groups like C2V. And I have excluded them for this reason. Okay, so now that I've explained all of that, let's assign some molecular orbitals to irreps of the point group, and we'll worry about the functions later. So let's start with an easy example to help this sink in. Let's look at ammonia, or NH3, which is in C3V. Here is its molecular orbital diagram. Here is its character table. Now let's assign them. For the first molecular orbital, under the identity E operation, nothing changes. The orbital looks the same. So the character is +1. For both the C3 rotations, so 120 degrees and 240 degrees about the z-axis, the orbital also remains unchanged. So again, we have +1. And under each 3 sigma v reflections, there's no change in phase or shape. So once again, we have +1. Adding up that pattern, we have +1, +1, +1, and that matches A1. For the next molecular orbital, for E, there are two orbitals that transform together. So with this orbital, the red ones and the blue ones transform and remain the same together. And the black one is simply a node, so it's nothing. So again, considering both orbitals stay the same, the sum of the unchanged orbitals is +2, therefore we have +2. Under either C3 rotation, the orbitals mix or swap directions, resulting in a combined trace of -1. And under any of the sigma V reflections, one orbital might flip, while the others stay the same. But if we add them all up, saying for example opposites cancel out, like adding 1 and -1, the sum or overall would be 0. So the character pattern is +2, -1, 0, and that corresponds to E as the irreducible representation. So to summarize so far, for the first two we have A1 and E. Now try pause the video and see if you can work out the rest. And a little hint is none of the orbitals in NH3 belong to A2, so they should only be E or A1. When you're done, the remaining set of ammonia's molecular orbitals correspond to E, A1, A1, E, and E. And there you have it. Those are the irreps for the molecular orbitals of ammonia. And that's all the examples I'll give today, as to not make this video too long, but I hope that made sense. As a practice exercise, I've included the molecular orbitals for methane or CH4 and the TD character table which it belongs to. So see if you can assign the correct irreps to each molecular orbital yourself. Otherwise, thanks for watching, and I'll see you next time.